So, welcome to today's lecture. Today, we will be continuing our discussion on matrix concentration inequalities. In the last class, we discussed a few applications to motivate the study of concentration bounds on random matrices. We looked at an example of the sample covariance matrix, and we saw that how it can be represented as the sum of independent matrices, and we used the matrix Bernstein inequality to study some properties of that of the sample covariance matrix. From this lecture onwards, we will slowly build towards the proof of uh, the matrix Bernstein inequality, and today we will largely be talking about the Hermitian matrices. Okay, so in today's lecture we will just be talking about random Hermitian matrices. Okay, so this is the agenda of today's lecture, and we will straight away uh, start with a proposition. Okay. So if Y is a random Hermitian matrix, then we can generate some bounds on it, tail bounds on it. Okay. So before going into the proof, it is always a good idea to just stare at the inequalities for some time, and to find out and to see if there are any familiarities with what we have already discussed. Okay. So here, when we write trace, when we write TR, it means the trace of the matrix. This is one point. And then the second point is that e raised to the power theta y is the matrix exponential. Okay, so it's the matrix exponential series behaves just like the scalar exponential series. I mean 1 plus y plus theta square y square by 2 factorial and so on. So these are the two things. Yeah. So now we come back to just looking at the inequality for some time and trying to see if it looks familiar. Okay. So here we need to find. So in the first inequality, let's say A. In A, we need to find the probability that the maximum eigenvalue of y is greater than or equal to 2. This maximum eigenvalue the maximum eigenvalue is the spectral norm, because the singular values and all those things, it is less than some exponential term, infimum, and all these things. Okay. So from what we have seen in our studies of Chernoff bounds and all those scalar inequalities, this infimum, it is when we studied the scalar inequalities, we differentiated, equated to zero to find the value of theta such that this bound is tight. So this infimum part, so this infimum So this infimum part is just for the optimization thing. Okay. So this is not really part of the bound, but just that given some specific metrics and for some special cases, we can actually calculate the infimum, and then thus this bound will be tight. So when we are looking at the bound, infimum means that value. E raised to the power minus theta t, e raised to minus theta t comes through from the moment generating function method which we saw earlier. Okay, because when we take the exponential on both sides. Okay, so we will do e raised to the power theta lambda max y, e raised to the power theta t, and when we take exponential on both sides and then when we apply the Markov inequality, we will have uh, e raised to the power theta t in the denominator. So if we apply Markov inequality, we will get something like this: e raised to the power theta lambda max y divided by e raised to the power theta t. And this we have seen in the scalar case as well when we were deriving Chernoff bounds, even for Bernstein, for the scalar Bernstein inequality, and we have done seen this trick several times. So this is how e raised to the power minus theta t comes into the picture. Okay, so this is sort of clear. Now the only thing that we do not right away understand is this term, that the expected value of trace of e raised to theta y, we have to connect, we we basically have to connect these two quantities that are marked in the red, because the other quantities infimum and e raised to the power minus theta t we already understand. We somehow have to draw a relation between trace of e raised to the power theta y and between the expected value of trace of e raised to the power theta y and the expected value of e raised to the power theta max of y. Okay, we can do the same analysis. So this is just an overview of what this inequality is. Before even going into the proof, we can just by eyeballing at the inequality, we can grasp as much. Okay, we can do the same analysis for the second inequality as well. This is infimum, this is e raised to the power minus theta t, and we have the same quantity here. But here, one thing which you have to notice is that we are looking at the probability that the minimum eigenvalue is less than t. So the maximum is greater than, and here we have a less than sign. Now, if we have to invert the sign, the a common thing to do is that I mean, the only way which we can do is that in this example we assume that theta is greater than 0. Therefore, it did not change the inequality sign, but because here we have a different inequality, we will do the same method, but we will take theta less than 0. Okay, because when we take theta less than 0, then the sign of the inequality will change. We will see later how it all works out. But this is just to give you an overview of how much we can see into the proof without actually doing the proof. But now that we have done that, now we will go into the actual proof. Okay, so we will first do the proof of A. So these are some usual steps which I will just write down quickly without spending too much time on it, because by now we all of us know how to do these things. Okay, so this is done. Here we have used the Markov inequality. So till now, I mean, these steps should be obvious by now of how we want to do this. Now, what we are left in the LHS is the expected value of e raised to the power theta lambda max y, and on the right hand side is the expected value of of trace of e raised to the power theta y. So if we informally, if we just have to write it down, so on the left hand side, we have expected value of e raised to the theta lambda max of y, and on the right hand side, we have expected value of trace of e raised to the power theta y. Okay, so we have to somehow create a connection between the largest eigenvalue of y, e raised to the power the largest eigenvalue of y, and the trace of e raised to the power theta y. One thing which we know as a fact is that trace is sum of eigenvalues. So why am I talking about eigenvalues here and not about singular values? Because we have a Hermitian matrix. I will leave it to you to prove that for a Hermitian matrix, there is an eigenvalue decomposition. Okay, so this is something. So we have, so trace is sum of eigenvalues. So if trace is sum of eigenvalues, then we do have a loose inequality that lambda max of y is less than or equal to trace of y. Okay, we can even do something like this. Okay, so we can even do something like this. So this inequality, because whenever we see what we want to prove, we just start with what we already know. So this fact we know by linear algebra, that trace is sum of eigenvalues. So theta times the largest eigenvalues will definitely be less than trace of theta times y. Okay, now what we have to prove is that when we take, now we have to work somehow with the exponential. Okay, so is where uh, here is where the analysis takes a slightly different turn. I mean, if you can see why this is true, then good for you. If not, then we will prove. Okay. So the left hand side, again, before trying to prove this, we will just understand, spend some time on it and see what it means. So the left hand side is a scalar. Okay, because largest eigenvalue of theta y is a scalar, and e raised to the power e raised to the power that thing is a scalar. So if we have to expand it, yeah, we'll do just a scalar thing. And here we are saying that uh, this is a matrix exponential. Okay, and we do calculate that matrix exponential, and of that exponential we will take the largest eigenvalue. All right, so if you want, you can pause the video at this moment and try to work out the proof yourself. I will also be discussing it, but try to work out the proof yourself by expanding both left hand side and right hand side in terms of the exponential series, and then just try to argue why LHS will be equal to RHS. Okay, so you can try it out yourself before looking it into the solution, because the proof is sort of elementary. Okay, so next we will look at the proof. So if we look at the left hand side is just we will just expand using the exponential series. And so on. So there is not really anything more that we can do with it. Then we do the right hand side. In the right hand side, we need to find the largest eigenvalue of the matrix exponential. So we will first evaluate the matrix exponential. Matrix exponential is can be calculated as follows. Okay, one thing which is there with matrix exponential is that the matrix should be a square matrix. Okay, so it should be obvious to you that why it should be a square matrix. If it is not obvious, then yeah, you can think more about it, that why it needs to be a square matrix. Then next, what we do is that since Y is Hermitian, okay, since Y is Hermitian, there is an eigenvalue decomposition. You should definitely try to work out the proof that if Y is Hermitian, what is the reason it has an eigenvalue decomposition. The easiest way to see is to find the singular value decomposition of Y and then the singular value decomposition of Y transpose and then compare both of them. Okay, uh, so this is one thing. And next is that when we evaluate Y square, this comes out to be identity, and we have, okay, so this is what we have. Similarly, we can find out the higher powers of Y as well. Now, when we substitute it back, the proof comes easily. So I is Q star plus theta times Q lambda and so on. Okay, so now when we can compactly write it probably in this way. Okay, now it will be a lambda here. Okay, so now when if we have to find the largest eigenvalue of this expression, then the largest eigenvalue of this expression is just, the largest eigenvalue of theta. Actually, we did not, we didn't need to uh, expand the left hand side. So it is easy to see that the largest eigenvalue of this expression is equal to, what is the left hand side? E raised to the power lambda max theta y. Okay, so the largest eigenvalue of this expression is comes out to be something like this. Okay, so the left hand side is equal to the right hand side. So we end the proof here of this claim. Okay, so this is the proof of this claim that e raised to the power lambda max theta y is equal to lambda max e raised to the power theta y. Now that we have proved this, we come back to this point. Okay, so what we have proved here is that e raised to the, okay, this is what we have proved, and we already know that this is less than trace, because trace is the sum of eigenvalues and all those things. This is less than the trace, and so when we take the expected value and all that, so when now we will substitute this equation here. Okay, so when we substitute this equation here, we directly get that the probability that the largest eigenvalue of y greater than or equal to t infimum, because we will minimize it for specific examples, we will minimize it. Okay, so this seems like a very rudimentary approximation, because one would imagine that the largest eigenvalue and the sum of the eigenvalue, this is not a very tight bound, but this works out in some specific examples, but this is just the starting point. Okay, next we will use the same for lambda min as well. Now we need to now we move on to the B part. For the B part, we need to prove that the smallest eigenvalue less than equal to t is equal to probability that okay, so but here we consider theta is less than 0. Okay, we start from this point, and then skipping one step, we reach here. Okay, so one thing next, we will use the relation from linear algebra that the smallest eigenvalue of minus a is equal to minus of the largest eigenvalue of a. Okay, so if you we can just look at it from an example, that if we have 1 0 0 2, to see how this works out, suppose we have a matrix 1 0 0 2. Okay, and here let's say we have minus 5 outside, so then lambda max of this matrix is minus 5. Okay, wait a minute, what I'm trying to say here is that uh, okay, so minus 5 times lambda min of this matrix is equal to minus 5. On the other hand, when we multiply minus 5 inside, then lambda min changes into lambda max, and we will have 0 0 minus 10. This also comes out to be minus 5. So here we will take theta, which is negative, inside the lambda min, and that will change lambda min to lambda max. Okay, so what we obtain with all that is that expected value of e raised to the power lambda max theta y. Okay, because we just moved theta, which is negative, inside this argument, and this we have already proved that this is in the first part expected value of trace of e raised to the power theta. Okay, so this is done. So the observation that we looked in the proof can also be generalized. So in the proof, we saw the observation that lambda max of theta y is equal to lambda max of, so this is what we saw. We can actually generalize these observations by introducing some more semantics. Okay, now we will generalize this particular observation. For that, we'll need some semantics, and the first semantic which we introduce is the definition of a matrix function. Okay. So let's say if A is a Hermitian matrix. Okay. So A is a Hermitian matrix. Now we define the standard matrix function f of A as f of lambda 1 till f of lambda n q star. Okay, so this is the standard matrix function. So when we say that f is a standard matrix function, then when it is applied to a matrix A, it applies in this way. So this is the definition of a standard matrix function. Okay, now this is not a completely arbitrary definition. If we have to find find a motivation or a justification for this, for suppose we have a scalar function f, a scalar exponential function. If it is defined in such a way, then if we have to create an analog for matrices, so we need the property that it should be something in this form, because we want to create an analog of the exponential something that of an exponential function to the matrices, we need the function to be something like this. Now we already saw that since it is a Hermitian matrix, and when we calculate A square, we will have q star q star, this goes into identity, and we will be left with something like this. Okay, so this is the sort of the motivation of why defining a standard matrix function in this form, it makes sense. It is just a definition. Now that we have defined the standard matrix function, we can go ahead and state what is called the spectral mapping theorem. Okay, so the spectral mapping theorem says that if f is a function from I to a real number, where interval I of the real line. Okay, so f is a function defined on scalars, sort of. Okay, then if A is a Hermitian matrix, because we have defined the standard function in that way, whose eigenvalues are contained in I. Okay, then the theorem basically says that if lambda is an eigenvalue of A, then f of lambda is an eigenvalue of f of A. Okay, so this is the spectral mapping theorem. Uh, I would like you to spend some time on the spectral mapping theorem and prove the result that we had earlier using this theorem. You prove this result that e raised to the power lambda max of theta y is equal to lambda max of e raised to the power theta y. Define what is f, how does it come through, and all those things. Okay, and using all the definitions, you might want to try and prove that. Spend some time on it. It will help you understand the material in a better way. So this is, I mean, these two steps, defining a standard matrix function and the spectral mapping theorem, this was just the generalization of the proof that we did, so that we don't have to do it again and again if and when we encounter such situation in future. Okay. So that is sort of the first, the discussion on the first part of the lecture, where we found out the tail bounds on the largest and smallest eigenvalue of a random Hermitian matrix. In the next part, we will derive exponential bounds for eigenvalues. Sorry, expectation bounds for the eigenvalues. So what we want to prove is that expected value of lambda max is less than or equal to infimum theta greater than 0 1 by theta log exponential trace e raised to the power theta y. This is the A part, and with the as we did in the previous part as well, when we do the largest eigenvalue, we also do the smallest eigenvalue. What is the expected value of the smallest eigenvalue? So this is greater than supremum theta less than 0 1 by theta log expected value trace exponential theta y. Okay, so this is that. Again, if we look at the inequality carefully before trying to prove it, we see here the first part is just to optimize the bound. Okay, because we have a greater than sign here, we want to find the supremum of the quantity on the right hand side. Here, since it was an upper bound, we want to minimize the upper bound as much as we can to tighten the bound further, and the remaining things they are as it is. Okay, so in the last part, in the previous proof, we had just the expected value of trace of e to the theta y. Okay, so this is what we had earlier. In the proof, uh, it would be good for your learning if you just pause the video right now, and with whatever we have discussed till now, try to prove it. Okay, the only thing additional that you will need here is the Jensen's inequality. Okay, so whatever we have discussed till now in this lecture, whatever we have discussed till now in this lecture, that and using Jensen's inequality, we will be able to prove this. Okay, so it will be a good exercise for you if you just pause the video and try to prove it yourself. And otherwise, anyway, we will be proving it here. Now we will go to the proof. So what we have already seen from the previous proof is this. Okay, this we have already proved. Now, if we put expectations in front of everything, then we got the previous proof. And we actually want to prove, pull the expectation here, because when we will have expectation here, expectation here, expectation here. But the additional term that we have in what we want to prove is the logarithmic term. Okay. Now, how can we introduce the logarithmic term before introducing the exponential? Is is I mean very simple. So what we can do is trace of e raised to the power uh, theta y. We will do something like this. Lambda max of y, because on the left hand side we have lambda max of y, is equal to 1 by theta lambda max of theta y. Okay. Now, because earlier we used the moment generating function trick, here we do not have any moment generating function. That is why the log term comes into picture. This can be written as 1 by theta log of, okay, so actually let me do it here one step below. So we have lambda max of y. This is equal to 1 by theta lambda max of theta y. This is equal to 1 by theta log of e raised to the power lambda max of theta y. Okay, and we know the bound for lambda max of theta y from here. So we directly substitute it to obtain 1 by theta log of trace of e raised to the power theta y. Okay, because we did not have, I mean, we just used whatever we did earlier. So what we are left with is finally what we obtained is this inequality. Next, we have to introduce the expectation. And we are almost done at this stage. That is equal to 1 by theta expectation of log of trace of e raised to the power theta y. Okay. Whenever we see expectation and we want to take the expectation inside the logarithm, we want to take the expectation inside this logarithm, and the inequality that we know for that purpose is the Jensen's inequality. Just to remind you, the Jensen's inequality, we had expected value of phi of x is greater than or equal to phi of expected value of x. So we had phi is convex here. Okay. For concave, we will have it in the opposite direction. Okay, and it makes sense. So log is concave. Okay, if you look at the definition, log is concave. So we will use the concave version of that result. So what we have is expected value of lambda max of y is less than or equal to 1 by theta. Expected value of log of trace theta y is less than or equal to 1 by theta log of expected value of trace of e raised to the power theta y. So that is that. This we have proved using what? So we proved it in two steps. In the first step, we used the tail bounds from the first part, and in the second step, we just used the concave version of Jensen's inequality. This second part, I will leave it for you to do, just for your practice, because I don't know if we will have a homework for practice or not. So the second part, since we already saw the second part for this inequality, so using the tricks from that, you can try attempting the B part yourself. Okay. So moving on. Uh, Till now, we found the expectation bounds or the tail bounds for a single Hermitian matrix. Now, what we are interested in is bounds for sums of independent random matrices. I mean, this is our end goal. So this was our end goal. Okay. So let us just recall what we did in the scalar case and if it can be extended as it is to the vector case, or sorry, to the matrix case, if and what problems we might face. So if we recall, what we did in the scalar case was very simple, that this is probability e raised to the power theta xi greater than or equal to e raised to the power theta t theta greater than 0. Using Markov inequality, we will have e raised to the power theta sum of xi. Here xi's are the IID, e raised to the power theta d. Then we said that this is equal to e raised to the power product of I, e raised to the power theta xi, e raised to the power theta t, and since xi's are independent, using all sorts of arguments, we came up to this point. Then to finish the proof, we just use the moment rating function of xi's, assuming it exists, and then we found a nice exponential bound for it. Okay, so this was the method that we used for the scalar purpose. Now let us try to do this the for the matrix case. Okay, so you might want to spend some time again on thinking whether which of these steps that we have used will get messed up when, or if it will get messed up when we try to do it for the matrix case. Okay, so the keys, you can pause the video now. Okay, so the key step in all of this is the jump from here to here. Okay, so when we wrote e raised to the power sum of xi as the product of e raised to the power xi, so what we did was that for scalar case, we can write something like this. Again, everything else just follows because these are independent. We can break down the expectation, then just calculating it once is enough, and all these things are follow. They just follow. Let us try to do this for the matrix case. So when we have to do this for the matrix case, we just go by first principles. As always, in this course, we have focused on first principles. So we'll just try to do this by first principles. Then if we look at the left-hand side, the left-hand side is okay. And next, we try to do the right-hand side. The right-hand side will be now when we multiply these terms, e raised to the power x1 into e raised to the power x2, we will just write the terms up to power 2. So we will have I plus x1 plus x2, because here we have 1 factorial. These two, so this will get multiplied by this, and this will get multiplied by this. So we will get by 1 factorial plus we will have x1 square plus x2 square by 2 factorial, because again identity multiplies x1 square, identity multiplies x2 square, we will get this, and then we will have x1 x2. Okay, and so on. So when we simplify this, we will have x1 plus x2 by 1 factorial plus x1 square plus x2 square plus 2x1 x2 divided by 2 factorial. So this, if we are not careful, uh, one would think that this works out, but there is a very subtle argument here, which if you are not careful, you will miss. this is not equal to x1 plus x2 whole square. Okay, so here we had x1 plus x2 whole square. These two quantities are not necessarily equal for matrices. This is the first observation. And then the second observation is that if we do x1, if we just reverse the order, then these things will be same. But the second order term which we will get is 2x2 x1 by 2 factorial. Okay, so again these two terms are not necessarily equal. It is because these two terms are not equal. I mean, in fact, they will be equal only when x1 x2 is equal to x2 x1. Okay, so when matrices are commutative, so we say that when the matrices are commutative. So the another reason to look at it is that x1 plus x2 whole square is actually x1 plus x2 times x1 plus x2. So this will give us x1 square plus x2 square plus x1 x2 plus x2 x1. So this is what we will get if we work everything out from the very first principles. So with all these considerations, we conclude that e raised to the power x1 plus x2 is equal to e raised to the power x1 multiplied by e raised to the power x2 is equal to e raised to the power x2 e to the x1 if x1 and x2 are commutative. So when we say commutative, we mean that x1 x2 is equal to x2 x1. Okay. So you might want to think that since x1 and x2 are getting added to each other, they are of the same dimensions. So when they are of the same dimensions, and since we are expanding it in series, x1 and x2 are square matrices as well. How is it possible, or can you think of a counter example when, despite being square matrices of the same dimensions, this is not true? Okay. One, if you can find it, it is good. But just give one example. If we have b is equal to 9 minus 2 minus 1, 3, then ab is equal to 15, 5 minus 23, 90, and BA is equal to 22, 17 minus 8 and 12. Okay, so AB is not equal to BA, therefore this method, it fails. Okay, so an important observation which we have made here is that using just the first principle, we have not used any sophisticated arguments, is that MGF trick may not apply, or let us just say may not work for matrices. Okay, so this is the important observation where there is a slight diversion from our analysis of scalar case to the analysis of the matrix case. Okay. So next question to ask is that, because remember that we are in the quest of finding the bounds for sums of independent random matrices, and with our experience, the experience that we have gathered, it is important to somehow break down that sum into simpler terms. Okay, so when we break it down into simpler terms, the math comes out easy and the bounds are easier to find and all those things. So we are just trying to discover a way that works. We saw that the MGF trick, it may not work. Then the next question to ask is that Because for the probability term, whatever we saw the bounds in terms of trace. So does trace work? So when we say trace, we we are just talking in a very flaky terms. In hand wavy terms, we have not yet talked about what does it mean that trace works. But never mind. Okay. So what we are looking for is that trace of e raised to the power a plus h is less than trace of e raised to the power a into e raised to the power h. Okay, equality is definitely not true in general. Equality is definitely not true because we can just quickly construct an example that 1 0 0 2, this becomes a, and we will have minus 1 0 0 minus 2, this will become h. So when we do a plus h, we will get all zeros. Okay, so the trace of a plus h and trace of ea, I mean, yeah. So I just tried to come up with an example on the go. Generally, when we have addition and if we want to find a counter example, it is a good idea to work out with the negative. And negative, first we try the negative part and then we try multiples and all those things. Yeah, so this generally this is true. This is actually this inequality that we have. It is a popular inequality and it is called as the golden Thomson inequality. Okay, we will not discuss its proof here because it is not in the scope of the discussion. It is an inequality that came up in statistical physics. Okay, we'll just assume that this is true and work with it. Now, but this is proven to be true only for two matrices. Okay, so this is not true. A plus H plus T is not necessarily less than equal to e raised to the power A. Okay, for certain A comma H comma T. All right. So at this point, you can pause the video and think about examples of when this inequality will be true and when this inequality will not be true. Okay. So example. Okay. So now since A is Hermitian. Okay. So here we have for all A and H Hermitian. Okay. Now one thing is true is that if we are analyzing this, if A is Hermitian, H is Hermitian, A plus H will be Hermitian. And using the Golden-Thomson inequality, we can write it in this way. Into e raised to the power t. Okay. So this is one thing. Next, what we know is that we can find a class for which this inequality is true. If, as we have discussed earlier again, if A and H are commutative, that is AH is equal to HA. This we have discussed earlier. Then it can definitely be written as e raised to the power A, e raised to the power H, and e raised to the power T. Because we can write e raised to the power A plus H as this. So here we have only proven that if A and H are commutative, then this inequality is true. It is not an if and only if condition. This is just a class of cases for which we can break down the sum. But then again, there might be some issues because we are considering three matrices. We need, let us just say, if it is not very obvious, so let's just say if A, H, and T are pairwise commutative. Okay, so any of these are, since addition is commutative, we can just switch the order. We do not want to get into those intricacies unnecessarily. Let us just assume that AST are pairwise commutative, then this will be true. But in general, it is not true. Okay, so the trace, uh, it does not really work out. Okay, so the trace trick also fails. Next, what we look at, I mean, the inequalities or the initial setup that we saw, it had a log in it. So we tried the MGF trick, the moment generating function trick. We tried with the trace. Next, we will see if the logarithm aspect it works out. So there is something called a cumulant generating function. Cumulant generating function is uh, in some ways similar to the moment generating function. What it means for scalars, what the cumulant generating function means for scalars is the log of e raised to the power theta xi. We do a calculation of this sort which we just saw earlier. Then we will have log of uh, theta xk. Then this can be written as sum of k log of expected value of e raised to the power theta xk. Okay, so this is how the trick works out in this scalar case. Now we want to see if the same trick can be extended to the vector to the matrix case as well. Okay, so this is what we want to see, and in fact it does extend, and in what follows we will look at some examples of how it extends to the matrix case. And the first step, not example, sorry, follow a particular method or a particular set of arguments where we can see how this idea extends to the cases, to the case of matrices. Next, we will discuss a very important theorem, that is Lieb theorem. Okay, Lieb's theorem. I do not know if we will be covering the proof of Lieb's theorem or not. I have still not decided on this, but for now we don't have to think about the proof. We will just look at the theorem and use it here, and later on, if and when we see it is fit for the class, then we can discuss the proof. Because if we discuss the proof of Lieb's theorem, it in itself might take 2-3 lectures. So I don't know if we have time for that, and the interest also, because it is sort of advanced matrix analysis. I'm not sure if there is enough interest. So let's so the statement of the theorem says that fix a Hermitian matrix H with dimension D, then the function uh, or we can also, yeah, h plus log a, trace exponential h plus log a. H is Hermitian. The function takes the argument a. Okay, is a concave map on the convex cone of d cross d positive definite matrices. Okay, so this is the statement of Leib's theorem. So it has some quite heavy words. We just want to understand the theorem first, or what it says. The first thing it says is that on the convex cone of D cross D positive definite matrices. And then the second thing it says is that concave map. Okay, we are not talking about what the map is. Let us just forget what is written about this blue line. Concave map on the convex cone of D cross D positive definite matrices. Okay. The first is we will first discuss the convex cone. Okay, so positive definite matrices are those for which U transpose A U is greater than 0. So when we say greater than 0, we mean that positive definite matrices are those for which all the eigenvalues are greater than 0. Okay, so that is, let me just confirm the definition of convex cone, if I remember it correctly or not. Okay, yeah, okay. So this is the definition of positive definite matrices. Next comes the definition of a cone. For those of you who have done maybe integer programming or convex optimization, combinatorial optimization. I don't know if this definition is covered or not. So we say that, I mean, just for completion, I'll just write down the definition here. A subset sorry. Uh, I'm just copying it from Wikipedia. A subset C of vector space V over an ordered field F is a cone such that if X is in C, then alpha X is also in C, where alpha is greater than 0 and it belongs to the field F over an ordered field and something like that. So we definitely can see that the set of positive definite matrices, they create a cone, because if U transpose AU has positive eigenvalues, then U transpose alpha AU will also have positive eigenvalues when alpha is greater than 0. Okay, so it definitely satisfies the definition of cone. Then next, we have to prove that it is a convex cone. So when we say that convex cone, it basically means that alpha x plus beta y belongs to C for all x comma y belong to C, and alpha comma beta greater than 0 for alpha and beta, they belong to the ordered field as well. So any linear combination of two elements, it also belongs to the cone. It is again easy to see that the uh, all the set of D cross D positive definite matrices, they create a convex cone, because we again can check that alpha A plus beta, let's say A prime U, is also greater than 0 if, okay, so you we can just verify this fact. And then the other thing it says is that this map is concave. Okay, concave, again we know the definition of convexity for convexity of a function. then we can define the concavity of a function. The main takeaway or how we will be using Leibniz theorem is that now that we have proved that this is concave, we can use Jensen's inequality. Okay, so this is why Leibniz theorem is relevant here. What we will look at next is that uh, we will use this inequality. I mean, we will just put expectations here and there, and because it is a concave Mach, we will take the expectation inside, and then we will prove the main result. Okay, that we will do in the next lecture, but I'll just give a statement of the main result, what we will be proving midway through the next lecture. We will be proving a statement of this sort: lambda max of k infimum theta greater than 0, 1 by theta log trace exponential sum over k log exponential e raised to the power theta x of k. Okay, this is just one part of the result, which we will be proving in the next class. But we can just look at how what the result means, or try to imagine the proof. This part is standard. We have an infimum here, which is also standard. Next, if we look at the sum of what we proved earlier for a single, I will also write down what we proved for a single variable case. When we have a single matrix, then we proved that lambda max of y is less than or equal to infimum theta greater than 0. Okay, so this is what we proved for these the single variable case. Okay, when we only have one matrix, single variable, when you say variable, actually we mean matrix. When we have only one random Hermitian matrix, then its eigenvalue is bounded in this way. We saw the proof, and we can also, in fact, if we want, we can also think about the flow of the proof. We start with the moment generating function, but because we cannot directly use the moment generating function trick, we took a log, then we took the exponential log, and then we did all sorts of things. Okay, so here the infimum part is common. 1 by theta log trace is okay. So just to make it look more familiar, I will write it this way. Okay, so 1 by theta log trace exponential was there, and we also have 1 by theta log trace exponential. Okay, so up to this point everything is same, but rather than having theta y, which was just one Hermitian matrix, we have sum of log e raised to the power theta xk. Okay, so this is the only difference which we have from that part to this part. In fact, if we only have one term, then it is easy to see that it will just be log of expectation exponential theta k. Then we can apply the usual convex Jensen and come back from there to here. I think it should work out. I have not worked it out myself, but yeah, but it should work out. Now for getting this term inside the proof, we will be using Leibniz theorem. Okay, because in Leibniz theorem we know that from a to trace exponential h plus log a, we is concave. Okay, so when we apply expectation here, then the expectation will go inside, will go here, expected value of log a. So this is what we will be doing, something around that sort, that sort of thing we will be doing. We'll prove a corollary, then we'll start off the next lecture again by revising Leib's theorem and then going ahead with the proof.